Hello and welcome to the next of the lectures in this 12th week of the course titled Approximate Reasoning Using Fuzzy Set Theory, a course offered over the NPTEL platform. In this lecture, we will look at one particular functional equation, that of the law of importation, and see how it enables us to obtain a computationally efficient procedure in getting an output from the compositional rule of inference. Let's begin by looking at fuzzy inference systems themselves. In the case of a single seesaw rule, we have this A implies B. This is the rule that is given to us. If you are using an FRI, all we need is a function f to relate the antecedent to the consequent and obtain a relation, and a composition operator. In the case of an SBR scheme, we need a matching function and also a modification function. If you have multiple seesaw rules, then we also need an aggregation function G in the case of an FRI, and also either the theta or the Fati inference strategy. Whereas in the case of an SBR, we will only need the aggregation function G as extra compared to having a single seesaw rule. Now, if you have a single meso rule, that means a rule where you have p dimensional inputs, a single rule where we have p antecedents relating to a single consequent. In the case of an FRI, we have this a bar indicating a multidimensional input. We only need a function f to relate the multidimensional antecedent to the consequent, and a composition operator. Of course, we need an antecedent combiner k to combine all of them to get a single relation. In the case of an SBR, again, we have this matching and modification function. Of course, we also need the antecedent combiner. In the case of multiple meso rules, not only do we need the antecedent combiner, we also need the theta or Fati inference strategy and the aggregation function G. And in the case of SBR, we need the aggregation function G and also the antecedent combiner K. Let's look at some of the functional equations involving fuzzy implications. Let's look at the basic families of fuzzy implications. The SN family, which is the SN implication. We know about the R implications, which we have discussed at length almost for more than half of this course. If you look at the functional equations, we have seen a couple of them in the previous lecture, which is the antecedent and consequent distributivity. But these are only two such. Of course, law of importation is one, but there are also many other functional equations involving fuzzy implications. For instance, x implies y is equivalent to negation y implying negation x. This is the contrapositive symmetry. So we could also think of this as a functional equation. This is another functional equation, I of x comma nx is equal to nx. And this is called the iterative functional equation, I of xy is equal to I of x, I of xy. This is the t conditionality that we have seen. This is called the hypothetical syllogism. We have kept it in the almost logical format because we could put I for the arrow and t for the ampersand here. But this is kept in this form so that we could see what exactly it is doing. It is essentially chaining inferences. P implies Q and Q implies R implies P implies R. So in some sense, it is a transitivity property. It is just what is called as a hypothetical syllogism in usual logic setting. There is also this inequality, I of xy less than or equal to I of x plus epsilon, y plus epsilon for admissible epsilons. This is called a speciality property. So we have these many different functional equations involving fuzzy implications and often another binary operation or unary operation. Of course, we also have the law of importation, which we have seen is like this. And we have seen in the previous lecture that for the major class of implications, we see that all of them do satisfy law of importation, and we have in fact characterized the T-norm with respect to which they will satisfy the law of importation. Now, why do we need to study such functional equations? Well, in the previous lecture we have seen it allows us to generalize many settings, especially the setting of inference mechanism itself, by allowing the implications to come from families outside of the R implication, but that's not the only utility of studying such functional equations. For instance, it is well known that distributivity equations, if an implication has distributivity property, then in the inference scheme that such an implication is being used, it can help in complexity or rule reduction. In the case of contrapositive symmetry, as we all know, it is very important in deductive systems and formal methods of proof, where you want to show some result. Instead of showing A implies B, you end up showing negation B implies negation A, the contrapositivity of the original statement. This is another functional equation which ensures that the synodality axioms of subsethood measure, which are used in image processing, will be valid. So an implication satisfying this functional equation is useful there. Of course, we know about T-conditionality, how it is important in generalized modus ponens of an inference scheme, especially when we discussed about a single CISO rule. This hypothetical syllogism is again useful in chaining syllogism in fuzzy systems. And this inequality, which is called the special inequality, such implications are called special fuzzy implications. They are shown to be useful in some data mining applications. Now the question is, what about the law of importation? Is it also useful somewhere? Of course, we have seen already in many places where this is playing a role in terms of monotonicity and robustness, interpolativity or continuity. However, now we are asking this question from the point of view of computational efficiency. We can always take solace in this quote of Nikolai Lobachevsky, who said, "There is no branch of maths, however abstract, which may not someday be applied to phenomena of the real world." So that means law of importation could also serve some purpose, not just in the theoretical or the correctness part of it, maybe also in the computational aspects of a fuzzy inference system. And that's what we will see in the rest of this lecture. Let's look at inferencing in CRI itself. Of course, we have seen this many times over. So if you have a rule of this form, if the temperature is low, then the fan speed is low. And if your given temperature is average, we want to obtain an output, fan speed is medium. So typically the rule is captured in form of a relation, and given an A dash, which is the input, we obtain B dash by composing A dash with R. Now, we have seen examples of it before, but once more, because it's the numerical aspects of it which will highlight the issue that we are going to discuss now. So given, let's assume that A and B, the antecedent and the consequent, are given as follows, as these fuzzy sets. We use the Gödel implication to relate them. So the relation would look like this. Now, if we are given an input A dash, all we need to do is use the sub T composition, which in this case, let's assume it's the usual minimum T now. So then what we obtain is this B dash. So we're using star to be the minimum T now. Now, what happens in the case of multi-input single output rules? So let's consider just one of them. We have seen this before too, that we need an antecedent combiner, and we don't then deal only with 2D matrices but also 3-dimensional matrices if we have two inputs. So if the temperature is low and humidity is high, then speed is fast. So now this is something like you have a fuzzy set A from f of x1, B from f of x2, and C from f of y. So x, or we could also take the domain to be x, y, and z. So normally what we do is we take the Cartesian product of A and B using a T-norm, and then apply the function f, which is typically an implication, to obtain the relation of this particular rule. Let's see an example. We have seen this before too, how to do this inference. If A is given like this, B and C are given like this, and let's use the implication for the f to relate the combined antecedent to the single consequent, and let's use the minimum T-norm for combining A and B into a single relation. So Tm of AB is essentially, once again, we are using the outer product concept. It's 0.9 and 1, it is 0.9, 0.9 and 0.6, it is 0.9, 0.6, 0.9 and 0.8, it's 0.8. The rest of the matrix can be filled like this. Now, the input, the antecedents themselves are multidimensional. So instead of having a single row vector, we are already having a 2D matrix. Now, this is what is going to play a role in giving us a relation with respect to the consequent C. So we have seen that this typically leads to a three-dimensional matrix, or in this case, three 2D matrices, because C has three elements. And we have seen that this can be split down into R of Zi for each Zi, where Zi is 0.1, Z1 is 0.1, Z2 is 0.1 again, and Z3 is 0.2. So how do we obtain this? Once again, we have seen this, that we take every element of Tm of AB and then use the implication with 0.1. So 0.9 and 0.1 is, we are using the Lukasiewicz implication, each one of them, and this is how we are obtaining the implication, the values of the matrix. Note that when we use the Lukasiewicz implication, so this is 1 minus x plus y, or 1 minimum of these two. So when you take 0.9 and 0.1, it is 1 minus 0.9 plus 0.1, which is 0.2. When we use 0.6 and 0.1, it is 1 minus 0.6 and 0.1, which is 0.5. So that is how we obtain this matrix. In the case of, so Z1 and Z2 are 0.1, so we obtain the same relation matrix, and Z3 is 0.2, so we obtain a different one. In some sense, translated by another 0.1. So addition of 0.1 comes into picture because Lukasiewicz implication is 1 minus x plus y. Now, so we have these three 2D matrices. Now, given an input A dash B dash, let's assume them to be singleton. Then what we do is, once again, we combine them using the antecedent combiner, which in this case it is the minimum T node. We obtain this and then use this to compose this 2D matrix with that 3D matrix. If you remember the analogy that we have given, we have three sheets, 2D sheets on which these matrices are, and the scheme of A dash B dash is another sheet. So we keep that matrix on each of these sheets and then in fact do the component wise min and then take the max. Clearly only this element will come out because rest of them will be 0. So 1 here, so only this component will come out, 0.5, 0.5 and 0.6. This is what we have seen. Right. This is how we do inferencing in a CRI when we have a single meso rule. Clearly we understand that when we have multiple meso rules, then it is getting even more cumbersome. Some of the usually cited drawbacks of CRI are as follows. Firstly, the computational complexity. Of course, it depends on the choice of operators employed, but let's look at it in terms of number of operations required. So now we have a p-dimensional input and a single consequent, single output. If you assume that each of the xi's of cardinality mi, that's a discretization granularity that we consider. Now first we need to combine these antecedents. Remember, if in the previous case we had two-dimensional inputs A1, A2 or A and B. So we got a 2D matrix. So now if there are M1 components on A1 and M2 components on A2, then it is M1 cross M2. Those many components have to be obtained to make the 2D matrix. So if you consider this, that means we need the product of this M1, M2, M3, so on till MP, so many operations to obtain the matrix itself. This is the antecedent component. The next, to obtain the relation between this combined antecedents and the consequent, we need another set. So total number of operations that are required is this. So Cartesian product of 1 to p plus 1 such operations. Now once again for the inference itself, given an input A1 dash, A2 dash, AP dash, once again these things have to be combined, which means these many operations, pi I is equal to 1 to p mi operations. And finally for the composition itself, we need the square of that operation. So if you assume that all the mi's are same, say is equal to m, then essentially what we are looking at is the order is given by the largest of this. So it is essentially, here you have m power p the whole square, so it is order of m power 2p. So those many operations have to be performed. So p is the dimensionality, m is the discretization constant, like on each domain, how many points of discretization, that discretization granularity that we are making use of. Now this is with respect to the computational complexity. What about the space complexity? How much we need to use as storage? So we need to store p plus 1 dimensional matrices for every fuzzy if then rule. So if you assume that the cardinality of x is m and y is n and z is l. So for the moment, let's consider only a 2 input, 1 output case. So m, n, z and l. So we have seen that to obtain the rule relation of the rule, we need a 3D matrix which will consist of m into n into l, those many elements, components. And towards doing the inferencing, first we need to combine the facts a dash b dash, which is again a 2D matrix with m cross n elements, and we need L to store the consequent. So essentially we need this much to hold it, m and L to hold the relation, mn to obtain the inputs and then find the matrix, and L to store the consequent. So once again, assuming that these are actually all same, that m is equal to n is equal to L, then this is for 2 input and 1 output, so that means this essentially becomes m power p plus 1, this m power p and m. So once again, taking the highest order quantity here, in general this is of order m power p plus 1. So for computational complexity is order of m power 2p, and space complexity is order of m power p plus 1. Now, why not perform the operation in a different way? So look at this hierarchically done CRI. What do we have? We have a rule of the form AB implying C, and we are given input A dash B dash. The hierarchical CRI, it suggests the following procedure. It says, first calculate B implies C. Then calculate an intermediate output C bar by using B dash and B implies C. So now B implies C means it's a single input, single output rule. You have a 2D relation. Given a B dash, you compose it with this R dash and obtain the C bar, which is an intermediate output C bar. Now in the third step, what we do is use A and this C bar as the consequent and obtain the rule relation. Then obtain the final output by composing A dash with this R double dash. So overall, this is what you will get. So at any point of time, we are actually only using a single input, single output rule, storing that, and then given the input, we are actually composing and obtaining this. And this could also be extended if you have 3 inputs or n inputs or p inputs. Now let's calculate this for the same values that we have considered. So the rule that we have is AB implies C and A dash B dash are the given inputs. Let's assume the same values for A, B and C. So first what we do is we obtain the relation between B and C only. B is the antecedent and C is the consequent. Once again, let us use the Lukasiewicz implication. So the relation that we would get is essentially this. Now to obtain the intermediary output C bar, we need to compose B dash with this B implies C, and we know B dash is singleton fuzzified. So when we apply this, what we get is just the middle row, which is 0.5, 0.5, 0.6. Now this procedure suggests that we should use this C bar as the current consequent and use A as the antecedent, and for this rule A implies C bar, we need to obtain the relation of the rule. Once again, using Lukasiewicz implication, this is the relation we get. And the final step says that take A dash, the given input, and compose it with this particular relation R double dash and obtain your final output. So once again, A dash is singleton fuzzified, which means it has a 1 only at the third element, which means the third row will come out. So this is essentially how we proceed. It is clear that we were able to do it in a single slide, which means it's much easier than what we have seen in CRI, even for a multi-input single output case. Not only that, there are very many advantages. The first advantage when you see is we need to process only 2D matrices at every stage, because we are only considering one consequent and one antecedent. So even if you have p-dimensional antecedents, at any point of time we are only taking AP with B, we get an RP, then we compose A dash with this RP and get a new, say, C1, then we will take AP minus 1 and then that B1 or C1, and then compose, consider them as an antecedent, the consequent, and get the relation. And then given AP minus 1 dash as the input, we compose it and we go on so on and so forth. So essentially, to obtain this single input and the single output case, we need only MP into L operations. Now to compose once again, this is what it means. So essentially it is MP into L operations. Note that at any point of time we are going to only consider single input, single output rules and a single input A dash or AP dash and obtain the corresponding consequent. So essentially all the time we are only using M cube operations, and we may have to do it P times. So the overall computational complexity is nothing but P times M cube. Compare this with the usual CRI, which is M power 2P. So it is clear that m cube is the one that is going to dominate depending on the granularity. So essentially it is m cube, and p if it is of the order of m, then it is m power 4 max, whereas here it is actually going to increase exponentially. What about the storage efficiency? You notice that at any point of time we are only storing the fuzzy sets of a rule, we are not storing the rule relation at all. So that means if each of the domains there is mi discretization, the number of points of discretization is mi, essentially sigma mi is what you need to store. And at processing time, of course, we need a relation and the given input and the given output. So essentially it is 2m plus m square. So order of m square is the highest thing that you will take. Compare this with order of m power p plus 1. So that's the difference in terms of storage. This is almost m square always, and that is m power p plus 1. And quickly it saturates exponentially. Not only computational and storage efficiency are available, we also have associative inferencing. For instance, if you are given this input, we can compose each of the AIs independently at every stage, which means we need not wait for all the inputs AI dashes, and also not necessarily in that order. So these are some of the advantages of having hierarchical CRI. But what about the inferred outputs from the original CRI and this hierarchical CRI? Even when we have the same A's, B's and C's and the same operations, we have noticed that from CRI, the output we got was 0.5, 0.5, 0.6, whereas from the hierarchical CRI it was 0.8, 0.8, 0.9, which is not equal to the original inference. Well, is it a problem? Well, yes, because we know that CRI, when we consider some operations, we have discussed at length about the desirable properties CRI has got in terms of interpolativity, monotonicity, robustness, and continuity. By moving to this form of an inference procedure, we should not lose them. So while we have a computationally efficient procedure, we should not lose the accuracy. Efficiency cannot hit efficacy. Now, is there an equivalence? Can we show that the outputs obtained from these two will be equivalent? Well, yes. Now, for that, look at the rule itself. So consider the 2 input single output rule. So to obtain the relation, what we do is we first combine A and B with a T and then apply an implication on this combined AB to C. So in some sense, this is how it looks like for any given triple XYZ. But now, what hierarchical CRI does is converts it into a sequence of implications. This is how it is seeing it. Now clearly, these two are equal if I and T enjoy law of importation. So if we have a result which says that if the inputs to the fuzzy system are singleton fuzzy sets, and if the antecedent combiner T norm T is such that the pair IT satisfies the law of importation, then the inference obtained from the CRI is exactly identical to the one obtained from hierarchical CRI. And what if the inputs are not singleton? Well, then essentially by using the associativity of T norm, which is like the law of importation with I substituted with T, we see that we could use the same T norm as the antecedent combiner and also to relate the antecedents and consequence, which is more like the R check rule. We see that CRI and hierarchical CRI inferences are in fact equivalent. So we see the important role played by law of importation here in ensuring that the computationally efficient mechanism is in fact also correct. In summary, we have studied law of importation in one of the previous lectures, and we know that there are many families of fuzzy implications which do satisfy this law of importation. We have seen that in the case of restricted lattices, it is always available, and we have made use of this multiple times in proving desirable properties of FRIs especially. But in this lecture, because CRI was computationally pretty inefficient, we moved to the hierarchical version of CRI for complexity reduction. However, we found that the outputs obtained from the hierarchical CRI were not equivalent to that of CRI, and that is where we found that the law of importation comes to a rescue and says, okay, if the operations involved satisfy this property, then we can ensure the output obtained from CRI is the same as that of what is obtained from an hierarchical CRI scheme.